Welcome to our lesson on dimensional analysis. Today, we'll explore the dimensions of physical quantities, how to deduce relations among physical quantities, and how to check the dimensional consistency of equations. Let's start by understanding what physical quantities are. Physical quantities are measurable properties of physical systems, like length, mass, time, force, and energy. Each physical quantity has a specific dimension that distinguishes it from other quantities. The dimension of a physical quantity expresses its dependence on the basic physical dimensions. The 7 fundamental dimensions in the International System of Units, SI, are length, mass, time, electric current, temperature, amount of substance, and luminous intensity. Now, let's explore how the dimensions of derived physical quantities can be expressed in terms of the fundamental dimensions. Derived quantities like velocity, acceleration, force, and energy can be expressed using the fundamental dimensions of length, L, mass, m, and time, t. For example, velocity is distance divided by time, so its dimensional formula is Lt to the power of -1, or Lt to the power of -1. Here are some common derived quantities and their dimensional formulas. Velocity has dimensions of length divided by time, Lt to the power of -1. Acceleration has dimensions of length divided by time squared, Lt to the power of -2. Force, according to Newton's second law, is mass times acceleration, so its dimensions are mLt to the power of -2. And energy, which is force times distance, has dimensions of mL squared t to the power of -2. One of the key principles in dimensional analysis is the principle of homogeneity of dimensions. This principle states that for an equation to be dimensionally correct, the dimensions of all terms on both sides of the equation must be the same. For example, let's check the dimensional consistency of the equation for the distance traveled by a body under constant acceleration, s equals ut plus 1/2 at squared. Let's analyze the dimensions. S is distance, so its dimension is L. U is initial velocity, with dimension L, t caret dash 1. T is time, so its dimension is t. I is acceleration, with dimension L, t caret dash 2. So the right side has ut has dimensions L, t caret dash 1 asterisk t, which equals L. 1/2 at squared has dimensions L, t caret dash 2 asterisk t caret 2, which also equals L. Therefore, all terms have the same dimension L, making the equation dimensionally consistent. Now, let's learn how dimensional analysis can help us deduce relations among physical quantities. Imagine we want to find a formula for the period of oscillation of a simple pendulum. We suspect it depends on the length of the pendulum, L, the mass, m, and the acceleration due to gravity, g. We can express this mathematically as t equals k times L to the power of a times m to the power of b times g to the power of c, where k is a dimensionless constant, and ab and c are the powers we need to determine. Let's analyze this dimensionally. The period t has dimension t, length L has dimension L, mass m has dimension m, acceleration g has dimension L, t caret dash 2, equating dimensions on both sides. T equals L caret am caret b, L, t caret dash 2, caret c, t equals L caret am caret b, L caret c, t caret dash 2c, t equals L caret a plus c, m caret b, t caret dash 2c. For the equation to be dimensionally consistent, we need from L, a plus c equals 0. So c equals, from m, b equals 0, from t, 1 equals dash 2c. So c equals -1/2 since c equals -1/2, and c equals a, we have a equals 1/2. So the formula becomes t equals k asterisk L caret 1/2 asterisk m to the power of 0 asterisk g caret dash 1 slash 2, which simplifies to t equals k asterisk sqrt L slash g. The actual formula for the period of a simple pendulum is t equals 2 pi asterisk sqrt L slash g. So our dimensional analysis correctly predicted the form of the relationship, with the dimensionless constant k being 2 pi. Now, let's see how to check the dimensional consistency of some common physics equations. First, let's consider Newton's second law, F equals ma. Dimensionally, F equals mLt caret dash 2, ma equals m asterisk Lt caret dash 2 equals mLt caret dash 2. Since the dimensions match, the equation is dimensionally consistent. Now, let's check the formula for kinetic energy. Ke equals 1/2 mv squared. Dimensionally, K equals ml caret 2 T caret dash 2, energy dimension. MV caret 2 equals asterisk LT caret dash 1 caret 2 equals M asterisk L caret 2T caret minus 2 equals ML caret 2T caret dash 2. Again, the dimensions match, confirming the equation is dimensionally consistent. Let's also see an example of a dimensionally inconsistent equation. S equals VT squared, where S is distance, V is velocity, and T is time. Dimensionally, S equals L, VT caret 2 equals LT caret dash 1 asterisk T caret 2 equals LT caret dash 1 plus 2 equals LT. Since L doesn't equal LT, this equation is dimensionally inconsistent and cannot be correct. Dimensional analysis is a powerful tool in physics that helps us 1. Verify the correctness of equations by checking their dimensional consistency. 2. Deduce relationships between physical quantities. 3. Convert between different unit systems. 4. Simplify complex problems by reducing the number of variables. Remember, any physically meaningful equation must be dimensionally consistent, which means all terms must have the same dimensions. This fundamental principle helps us avoid errors in our physics calculations and can even guide us toward discovering new relationships between physical quantities. Thanks for watching our lesson on dimensional analysis.